The mathematics of general relativity is not at all difficult, neither it is complex. You don't have to be a mathematical genius to know them. The mathematics of general relativity is very methodical, structured, scientific and systematic, and this keeps you thinking and bothering. It is so very difficult. Well, if you learn the structure and the steps to approach the mathematics, you will master them and have a clearer view of this wonderful theory of Einstein. In this video series, you will be learning what mathematics you need to know, why you should learn it, I mean to say what is the objective, what are the significant parts that carry relationship with general relativity, and finally, what are the best books and what are the best methods in learning them. You will be surprised to know that you already know a certain amount of mathematics that is required. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first episode on a series of episodes yet to be covered on how to learn the mathematics for general relativity. Well, first we start with this question, that what is general relativity? General relativity, also known as the General Theory of Relativity, was developed by Einstein and others, and it is known as the theory of gravity. It is a geometric theory of gravitation published by Albert Einstein in 1915. It is the current framework for understanding gravity in modern physics. We can say that it is actually a refined way of defining general relativity in terms of Newtonian mechanics, or you can say general and special theory of relativity refines Newtonian mechanics. So here, as you can see right on this illustration, that as it refines Newton's laws of gravitation by describing gravity by a geometric property of space and time. So the concept of the gravitational equation, where G is the gravitational constant, extends to something which is known as the four-dimensional space-time manifold on a technical front. And this goes back and extends further into cosmology, where we try to define things like a white dwarf, neutron star on a black hole, and these are extreme predictions using Einstein's field equations, which extends the space-time manifold into further cosmological structures. Specifically, it states that the curvature of space-time is directly related to what we call the energy and momentum of matter and radiation. So the straight lines that we calculate in our young days or in the school gets extended to what are called geodesics, which we are going to learn what they are and what is the mathematics that is required to learn. The relationship is defined by Einstein's field equations, and here, as you can see, time and space, which was considered to be two different identities, was unified into what we call as a space-time manifold, or a four-dimensional space-time manifold. And Einstein's field equations, the relationship is defined by Einstein field equation, a system of second-order partial differential equations, and this is what is called a stress energy momentum tensor, and various other mathematical notions which we are going to explore. So overall, what we can say is that it gives us a scope to further study cosmology, black holes, gravitational time dilation, and what is called gravitational waves. And thanks to LIGO, that we can actually detect and find out experimentally what are called gravitational waves. So from here we get a fairly good idea what is general relativity. It is a theory of gravity developed by Einstein and others, including Marcel Grossman and few other physicists, and it actually refines Newton's theory of gravitation into a much deeper and profound theory, which is called general relativity, where straight lines exceeds into geodesics and the curvature of space-time is being calculated using Einstein field equation, tensors, differential geometry, and various other things. Now, if we have a look of those illustrations, which is very common in the internet, then some people might say, no, these are not correct, etc. General relativity is something more mathematical. But what I would say, this one is also correct, this one is also correct, and this one is also correct. because all this diagram gives a fairly intuitive and a pictorial idea of general relativity. And what these diagram tells? It tells that there is a heavy object, it creates a dent, and this dent is basically on a kind of a grid. Now, considering that the question is that how do we understand that there is a heavy object and it is creating a dent, and what is that grid all about? Let us look into the next part of the video, where we are going to understand deeply a little bit of the definition of general relativity and how does it take it forward. Now, you open internet and go to Google and you type out what is called classical physics. You will find this kind of a, I would say, illustration. If you type out quantum physics and go to the images section, you will also see this kind of a, electron proton growing around a nucleus. So you will find this kind of illustration which defines classical physics and quantum physics. Now, one thing is important is that it does not show anything related to geometry, isn't it? Classical physics is shown by a pendulum, quantum physics is shown by electron and proton going around a nucleus. It shows more of the physics part, but it never depicts anything related to geometry. On the other hand, if we look into what is called general relativity, then we see something like this. And the overall picture shows a different depiction. It shows a geometric nature of physics rather than a pendulum oscillating to and fro, and the quantum physics where the microscopic particles are going around. So from here, what we understand is that what causes this kind of a curve and what this picture actually means. So then we can understand what is general relativity, and this is the objective of our learning, that how to learn. We are actually willing to learn the mathematics. The question is that how to learn this type of a grid, why it is causing a dent, how to measure that dent, what is those grids all about. So from here, what we can basically get an idea is that it is a study. So this is the overall picture showing a depiction of physics in geometric nature. Now, if we go to I would say, go to Google and type out what is general relativity, the keyword, and you will first come to know about space.com, which tells general relativity is a physicist Albert Einstein's understanding of gravity. You go to Wikipedia, it will tell in details that it is also known as the General Theory of Relativity, etc. So it is the geometric theory of gravitation pushed by Albert Einstein in 1915 and describes the gravitation in modern physics. You go to Britannica, you will see it tells that it is a part of wide-ranging physical theory of relativity. It was conceived by Einstein in 1916. General relativity is concerned with gravity, one of the fundamental forces in the universe. Then you go to New Scientist and it will also tell you that Einstein's general theory can be summed up in just 12 words. Space-time tells matter how to move, matter tells space-time how to curve. So overall, after looking all to 1, 2, 3, 4 definitions, what we can understand is that it is a study on the curvature of space-time caused by the presence of mass and energy. So we get a kind of a shift from our classical understanding that it is basically the study of the curvature of space-time, and we are actually studying the curvature which is caused by the presence of mass and energy. Now, because it is a curvature, and how do we measure the curvature, we come to the next most important part of our video, which is called a geometric understanding of space-time. Now, what do we mean by geometric understanding? We will come to that, but we will understand in this part that it is more of a geometry, and then we have to be well equipped and well prepared with the mathematics that deals more with the geometric understanding. Now, if you consider special theory of relativity, which most of you by this time you already know, then special theory of relativity deals with what is called inertial frame of reference. It deals with speed and velocity, which are experimentally provable, and it has got a certain frames of reference. This is, I mean to say, all about, in short, what is special relativity. So what we can say from here, it is a study of relativity and simultaneity. Obviously, because these deal with simultaneity. And from here, we can deduce this kind of a conclusion that it deals with speed, time, and space. Whereas when we consider general theory of relativity, we see that it deals with non-inertial frames, gravity, geometry of space-time, and it deals on a cosmological higher scale dealing with supermassive black holes, etc. So from all those 1, 2, 3, 4 points, what we can understand is that it is more of a study of a geometry, and this leads to the conclusion that it is a study of surfaces and curvatures. And that is why we tell that general relativity is less of relativity and more of geometry. Remember that this is a geometric understanding of space-time. We are doing this so that we can now understand and take up from here that what is the mathematics and how do we do and what are the mathematical tools that we have in our hand. So from here, if you see whatever the relativistic effects of special relativity, like length contraction, time dilation, whatever we had, when it got extended or when it got generalized into this kind of a illustration, which is called the curved space-time. And this generalization led to a huge paradigm shift in the understanding, and that is a paradigm shift from relativity to geometry, a paradigm shift from a complete change of the mathematical tools, and a paradigm shift of our understanding of coordinates, which totally changed. So we are approaching towards an understanding of more of a geometry which deals with curvatures, etc. And these are more of a geometric understanding rather than relativistic understanding. So this is the first thing that you have to keep it in mind, that we will definitely deal with a lot of mathematics, but unlike relativity or special relativity, we are dealing with the curvature and the geometrical and internal and external structure of space-time. So here, as you see, the length contraction, the time dilation, transformation of Maxwell's equation, mass energy equivalence, and speed of light, taking on the left hand side the tenets of special relativity, the tensors, geodesics, parallel transport, Riemann curvature tensor, and the other curvature tensors. Don't worry, if you don't understand, we will explore them one by one exquisitely. All these are nothing but a transition from relativity to geometry, and it is less relativistic and more of the nature of space-time. This is a kind of a prelude to make you understand and make you motivated and prepared that what kind of mathematics that we are going to do. It is not just we do the mathematics without knowing the reason why we are doing it. So the general theory of relativity is more of a geometry rather than relativity or simultaneity, and it primarily deals with geometry as the intrinsic nature of space rather than an extrinsic object. We will come to what do we mean by intrinsic and extrinsic slowly in the further episodes of the video, but for now let us understand all these things which are technically a little bit stringent to understand: parallel transport, covariant derivative, Christoffel symbols, geodesic, stress energy tensor, even to the cosmological scale, Schwarzschild solution of black holes. All these are getting now changed to what we call a geometric understanding of curvatures, and these are more intuitive in nature to imagine, and that is why we need some kind of an exotic mathematics. So this sets the stage, this sets the motivation, this sets you what is coming forward, that you are understanding a geometric nature rather than what you learned in special relativity. And this requires what is called a kind of a mental preparation. And from that mental preparation, we will guide and we will move into what is called the mathematical preparation. So if you are not mentally prepared, suddenly if somebody gives you mathematics, you are puzzled, you are foxed. So the mental preparation is that you need to learn and absorb a lot of geometry first. Jumping directly into mathematics like tensor calculus, please don't do that, because that is the biggest mistake. You should be able to visualize a lot of things, because geometry is all about visualization. So you will be tested on your visualization abilities, and you will be conceiving a lot of abstract ideas. Don't worry, I'm not making you a little bit pessimistic, but rather very optimistic, so that you know what is coming in front of you. So the visualization factors, why? Because it is all about geometry, and geometry relies on what is called visualization. So from here, what we can see that 4 important things emerge. First is an abstract power of visualization. There has to be a lot of logic, and there will be geometric transformation, because it is all from the general Euclidean space to what is called the non-Euclidean space. So you need to have an intuitive mind, or you should be thinking from now on intuitively, because general relativity is more intuitive rather than being mathematical. And in order to do all the visualization of abstract things, and you have a strong logic and geometric transformations, the first thing that you need to do is the mathematical tool that you need to have. And that mathematical tool is nothing more than what is called a calculus, single and multivariable calculus. Now remember that we are learning calculus, we know calculus, we solve, but in this particular video, in this part, we are looking also into why we are learning calculus, what actually relates calculus to the physics concepts of general relativity. Let us look into that, calculus and how it relates to general relativity, coming up to the next part of the video. So why you need to learn calculus to understand general relativity? So that is why I told that we do mathematics without understanding why. So the first thing is that calculus is very fundamental, because you will see that it is extensively used in describing the curvature of space-time. Calculus, as we know, that it actually marks what is called a change, and there are a lot of changes which happens in general theory of relativity. The first thing is what is called the geodesic equation. Don't worry, I'm not going to explain each and every part, but the geodesic equation, as you can see right on the screen, is a second order differential equation, and calculus provides the foundation of understanding these equations. It equips you with concepts of differentiation and integration, and these are essential concepts for manipulating and analyzing this equation. Geodesics are curves that extremize the space-time interval. Calculus provides the tools to find this extrema using techniques such as the Euler-Lagrange equation, which are fundamental in deriving geodesic equation. As the geodesic equation is derived from the Euler-Lagrange equation applied to the space-time interval, leading to a set of second-order differential equation. This one, as you can already see, this is what is called the Schwarzschild metric. We will come to that later, but as you can see, this is extensively containing calculus. And here you can see that the Einstein field equation, which is the core, actually the core of general relativity, is nothing but a collection of 16 partial second order nonlinear differential equations. So from here we actually know that these are the equations, or these are the reasons, geodesic, Schwarzschild metric, etc., that leads to the understanding of geodesic equation. Now remember that when you're learning general theory of relativity, you need to learn more of the partial differential equations. The reason is that partial equations means that there are more than one variable, and obviously general relativity, because it deals with space-time, that is 3 coordinates and 1 time, it would deal with partial differential equation. Einstein field equations, biggest example. It is a 16th order second order nonlinear differential equations which are reduced to 10. Also you will see the Newtonian partial derivatives of the gravitational potential can be actually taken into as partial derivatives of the metric. Now I actually don't want to go into this because this is a different video. If you go to my playlist in General Theory of Relativity, you will find this derivation in one of my videos. So you can clearly see evidences and examples of using the del and partial differential equations very much in Einstein's theory. Now another thing which becomes very important is what is called the Christoffel symbols. Now I don't want to become very technical, but just to tell you, Christoffel symbols involve derivative of metric tensor components, and a deep understanding of differentiation includes partial derivatives, which is crucial to compute these symbols accurately. Christoffel symbols appear in the context of what is called the covariant derivative, which extend the notion of differentiation to curved spaces. Covariant derivatives are fundamentally about applying differential operators in a curved context, a concept well understood through partial differential equations. So knowledge of PDEs involving with various differential operators like the Laplacian, gradient and divergence, all of these have analogues in geometric contexts where Christoffel symbols are used. So as you can see here that this is the first kind and second kind. I will explain it later, but it extensively uses PDEs. So that also proves that we need to have a strong understanding of partial differential equations. So here is the summary. To describe how vectors and tensors change from one coordinate to another, general relativity uses Christoffel symbol, and these are nothing but partial derivatives of the metric tensor with respect to the coordinates. I will show you something very unique, and I will show you also the video in which I have done. These are what are called the derivations of the metric tensor. Don't worry, don't get afraid about those big calculations, but these are actually basically derivations of what we called the metric tensor, and these actually leads to this part, and this is nothing but what is called the derivation of the metric tensor. So you can see basically on the screen that there are huge number of second order partial derivatives which are actually happening, which are actually going on, and these are basically derivation of the same metric tensor. As I turn the page, you can see here that ultimately the ds square, which is the metric tensor component, the line element, ultimately will come to this. So what is the gij and why it is upstairs and low, why it is downstairs, all those things we will let you know, and this will come in the subsequent episodes of the video, don't worry. And if you really want to know how this has arrived, this is the video which you can check in Metric Tensor and General Relativity, made a few years back, but this is a good video, and here you will come to know how extensively I have used partial differential equations in order to do the derivation. So from here you can also see that these equations also are simple, the Jacobian, etc. These are all using partial differential operators. So here you can see this is also another derivation of metric tensor, and this prime, you might be wondering what is this prime. So these prime are nothing but these are the transform coordinates, as we say the transforms are denoted by prime, and the blue ones are basically the unprimed coordinates, that means the original coordinates. So that actually establishes the proof and the point that you need to learn more and more of PDEs rather than ODEs. Now you might have a question in your mind that what are the concepts? We understand that we know PDEs, but what are the concepts? I mean to say, which are the major concepts of partial differential equation that carries more relation with general relativity? Obviously, and this will give you a motivation that these concepts you need to emphasize more and more and more, because these are the concepts which will take you directly from partial differential equations to general relativity. So which concepts of PDE relate to general relativity? Coming up into the next part of the video. So the first thing are which is called linear as well as non-linear PDEs. Now as you understand that general relativity involves both linear PDEs, because under weak field approximation, if you I mean to say under static low moving objects in a dust field, etc., if you recalculate the general relativity, it goes back to Newtonian mechanics. So that is why we need a linear PDEs for what we call linear calculations, and non-linear obviously for the full understanding of Einstein field equations. So the linear PDEs are required for weak field approximation, where you can assume certain things and you will see it goes back to Newtonian mechanics, and non-linear for the understanding of the Einstein's field equation. Now this is pretty important, what is called the elliptic, parabolic and hyperbolic equations. Now why it is important? Because the PDEs helps categorize the types of equation which are encountered in general relativity. Now in general relativity, the wave equation, which will be the gravitational waves, is hyperbolic, while the equation describing the equilibrium of a star might involve what are called elliptic PDEs. Because we are transiting from a flat Euclidean space to a more I would say complex hyperbolic coordinate system. So elliptic, parabolic and hyperbolic equations will be very much important, and Minkowski space diagram itself is a big I mean to say this is a big what I would say that that is a big proof. So hyperbolic equation, the Minkowski space, the light cone itself are all depending on this elliptic, parabolic and hyperbolic equations. So PDEs will become very pertinent and important on that. The next thing which comes are what is called boundary value and initial problems. These are important because solving PDEs with specific boundary and initial conditions, because initial value for the Einstein field equations predict the evolution of space-time. And this is very important, which is called analytical solution, because remember that today we use computer, but during that time 1915, 16 to 18, it is impossible even now to find an exact solution of Einstein's field equations if you are not given a Schwarzschild metric or a Kerr matrix, so on. So in order to do that, finding exact solutions, because it is difficult, Schwarzschild solution describes a space-time around a non-rotating. So I mean to say that the analytical solutions, if you learn analytical solutions, that becomes very important, and you will understand that how analytical solutions are used in Einstein's field equations. The stability and well-posedness, where I'm trying to mean, is that it ensures that the solution of PDEs are stable. That means these are the stability analysis under what we call very small perturbations. And existence and uniqueness of theorem, because these theorems deal with existence and uniqueness of solutions that come under PDEs. So if while not directly applicable to solving Einstein field equation, these theorems provide a foundation for understanding the properties and what are the potential limitations of these specific approaches. Last but not the least, very important is the Green's function and integral transforms, because you can search in internet and archive.org. You will see there are a lot of papers which are written using Green's function to solve what is called linearized gravitational field equations in weak field approximation. And this was just what I was talking to you in the first part, that linear and non-linear PDEs. So you need to have Fourier, Laplace transform and Green functions in order to use them to solve linearized gravitational field. So the point here is that by focusing on these specific concepts, you can gain a deeper understanding of the mathematical framework underlying by general relativity, and you can also take a step forward in order to understand more advanced PDE topics. But as of now, this is quite good enough to understand. Now we understand what are the relation, what are the primary concepts of calculus, why we need calculus, more importantly the PDEs. Now the question rises that how will you learn? Where are those functions? Where are those theorems? So we come to the next part of the video, which are called what are the books on calculus. Remember, there are innumerable books available, but I have just jotted down what could be the easiest and the best part of the learning. So the first book would be something like this, which is called Thomas Calculus, although it is mentioned early transcendentals, but this is a pretty good book. I would go by the Amazon rating, that is okay, 5-star, but I would give 90 or 95% 5-star, and I will tell you the reason. Now this book is, I would say, one of the best book and teaches everything that you need to know calculus. You really don't need to hop around to find some other books. It covers everything that you need. The book actually contains a lot of simple illustrations, examples, diagrams, and most importantly, what I always tell in my videos, that it assumes that you know nothing and goes deep in making you understand everything. So one-stop book, I think it is around 1064 pages, but as I always tell, that a big fat book is better than a thin slim book, because a slim book will assume a lot of things, but it will take you right from the grassroots level and take you and make you understand everything about calculus. Here are a few pages from the content of the book so that you understand what it covers. So it starts with functions, then go to derivatives, and it also teaches you, very importantly, limit and continuity for more than 55 pages. Integrals are covered in details with beautiful diagrams, graphs, charts, etc. The derivatives are also covered with infinite sequence and series. So these are, and you can see there are questions to guide, practical exercises, and it is just an awesome book to go. You will also see that it covers vectors and geometry of the space. So you will also learn this part, integration and vector fields. Most importantly, what we are talking about, partial derivatives, quite in details, along with that the multiple integrals. So this one book will actually teach you everything, although I will tell you more about the PDEs, because general relativity is all about PDEs, but this one-stop book of more than 1000 pages will give you enough good and a sufficient understanding about calculus. The next book is pretty simple. I mean to say, this is just for those who have started and you are a self-learner. Sylvanus Thompson's book on calculus made easy. It is very simple, but remember, it does not contain much about PDEs. If you're taking a first step in learning calculus, this is a must-read book. It is perhaps the most and the simplest explanation of calculus. So you can just read it. It is available in gutenberg.org. You can just download it. It is free. So it would be a great book to take a step ahead in calculus. This is a much more serious book and a much more mathematical book, Differential Integral Calculus by the great Soviet mathematician N. Piskunov. And this book has got 150 to 200 questions, which offers a perfect blend of easy and advanced problem. Piskunov also goes forward and explains the fundamental concept with rigor, probably one of the best introduction to calculus. And Piskunov's book is the ultimate source because for mastering single variable calculus, and it is one of the most comprehensive treatments of the subject. Remember that not much of PDEs are covered over here because this is the best book in terms of single variable calculus. Now, from Piskunov and from Sylvanus Thompson, as well as from the Thomas Calculus, we come back to one great book by an Indian author, and that is K. Sankara Rao's Introduction to Partial Differential Equations. Why I consider to be good? Because it gives a very clear concept and many problems you can solve. Even you can use it for your NET GATE examination. This is one of the best book on partial differential equations, and most importantly, it is a very user-friendly, good concepts given together with clear and easy explanation. Remember, because the video is all about learning the mathematics of general relativity, so obviously stress would be more and more on the PDEs rather than the ODEs. What are the basic content covered in this book? Here is an understanding partial differential equations of first order. Then the elliptic, as I told you, elliptic differential equation is very important. Parabolic differential equations, hyperbolic, and that it covers up Green's function, Laplace transform method, and Fourier transform method. So overall, whatever the major parts of PDEs that are required is being covered over here. The next book is equally exciting. And this book is written by two authors, Yehuda Pinchover and Jacob Rubinstein. I don't know whether you're aware about Yehuda Pinchover. He's a great mathematician. Now, these are the two pictures which I have, photographs I have taken. So overall, what I can say is that this book is very much to the point. There is a huge number of nice exercises, and I would say that you can go to the author's web page also to select it out, check it out. And this book is well explained, and each of the two authors allow a persistent student to gain in both their skills and confidence. Why I'm telling confidence, once you read, you will understand. And this is a little bit details about Yehuda Pinchover, Introduction to Differential Equations, and he is basically a mathematician. And this is his Google Scholar page, so that you really understand that who is and what is the authority of writing these books. So a quick glance over Yehuda's book, though it will start with introduction, first order equation, second order linear equation, then it will go into one-dimensional wave equation. Remember, while you are selecting partial differential equation books, you should be careful because a lot of PDE books use a lot of engineering concepts like heat, wave equation, etc. So if you're not willing to learn much of engineering concepts, you should select a book which is more mathematical in nature and describes and believes in building up the concept. So here also, Sturm-Liouville problems and elliptic functions are dealt with. Then you will find more equations in higher dimensions, the Laplace, the heat, the wave equation, the variational methods, the numerical methods, and so on. And finally, you will also see this book, which is very, very important, which is called Introduction to Partial Differential Equation. Now, this is a Springer edition written by Peter J. Oliver, and this is exclusive to PDEs. But what I found very interesting about on this book is this one. Easy to follow, most importantly. It is very straightforward. It includes weak solutions, nonlinear PDEs, Burgers theorem numbers, and numerical methods. And it is an excellent for those who are doing a self-study. And I will also recommend checking out the author's website for videos on PDE evolution. This is tremendous. You can go to the author's website and you can find it out. So it is a very good book for self-study. And when I talk of self-study, it means that it should be exhaustive. So here are a few of the glimpses from the content. So again, what are partial differential equations? It would start basically building on the concepts, linear and nonlinear waves, Fourier series, change of scales, etc. Then it would move into separation of variable, finite differences, generalized functions, Green's function, which I told why it is important in general relativity. Fourier transform, then it will go into linear and nonlinear evolution equations, followed by a general framework of linear for partial differential equations. Further, as you can see, that finite elements of weak solutions, which is important for general relativity, is also being covered. Elliptic solutions, heat equation, partial differential equation in space. So it's quite a detailed book. I think goes up to 656 pages. And most importantly, in the appendix section, you will find a little bit of linear algebra also, with a basic understanding of vector space, inner product, orthogonality, linear iteration, all those things. So along with this Peter J. Olver's book, which is very exhaustive, I can recommend two more books which you can go. That is Nackel H. Asmar's partial differential equation, and this is partial differential equation which is used by Ioannidis and Stepan A. Terzian. You can pick it up. But other than that, if you're not even going through the rest of these two books, these books are good enough. So now that we understood the reason why we should take up calculus, how and what are the concepts of PDEs that are related to general relativity, and most importantly, what are the best books, easy books, emphasis on partial differential equations. Now we come to the end where we draw our conclusion, and that is also important. Now when the question comes that why do we need PDEs or calculus or whatsoever, we can say it in this way. Because Einstein's field equations are a set of 10 partial nonlinear differential equations, because PDEs are used to express the relationship between stress tensor and Ricci curvature tensor, because many solutions to the Einstein field equations are found analytically and require numerical methods, and because it involves a four-dimensional space-time, that means more than one variable, and because by solving these PDEs or specific situation, scientists can find out how space-time is being curved, and the curvature in turn dictates how objects will move. So we can draw the conclusion that is why we need to learn partial differential equations. So that's all for today's video, and I have told you that it will be episodic one by one. So first part dealt with what is partial differential equations and how it relates to general theory of relativity. But remember, there are at least four more episodes coming up on the mathematics of general relativity, and I will unveil those secrets one by one. So thank you very much for watching this video. If you have liked the video, please click on the subscribe button to get all the notification from Physics for Students. You can write to this email ID of mine, and also you can subscribe to my other channel, General Relativity Explained. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with many more videos as well as this episode on how to learn the general mathematics of general theory on relativity will carry on until we complete it and have a comprehensive understanding of the mathematics. Till then, goodbye.